Hi everyone. In today's video, we're going to talk about collapse and self-supervised learning. We're going to run some experiments and do some analysis to see what went wrong with the self-supervised model. So first thing to know is what is collapse and self-supervised learning. There's a good definition in this paper, understanding dimensional collapse in contrastive self-supervised learning. If you jump right here in section 3, dimensional collapse. Self-supervised learning methods are used for representation by minimizing the distances between embedding vectors from augmented images on its own. So if you don't modify anything, just two encoders taking two augmented views and producing two embeddings, this would result in a collapsed solution where the produced representation becomes constant. If the two encoders are producing constants, the difference between these constants will be 0. If you average that, it will be 0. The sum of that will be 0. Then this loss will be 0. So this is where the name came from, collapse. Basically, the loss will collapse into 0. This is what we are trying to avoid. We don't have labels to optimize for. We only have the two encoders producing two representations. And this is a nice figure. This is a complete collapse. Both encoders are producing a constant or a dimensional collapse. No, you're not utilizing the whole space. So this is a 3D. Everything is projected into 2D. Here they continue to say contrastive methods prevent complete collapse by a negative term that pushes embedding vectors of different input images away from each other. This is why in contrastive methods are picking positive pairs and negative pairs. But in the most recent SSL models, IEEE, the dynos, they are not using negative pairs. So they are more vulnerable to have complete collapse, but they have solutions to prevent the collapse. So I run a small experiment to see what is collapse in self-supervised learning. You can find the code in this blog post. I'll link it below in the description. So acknowledgement to the authors of Dino V2 on IEEE because I borrowed some code from there. These are the references. This is Tim Siam paper. This is direct CLR paper. And this is a paper called On the Importance of Asymmetry for Siamese Representation Learning. So in summary, what I'm trying to do is just importing CIFAR-10 and running two vision transformers to see if we can collapse. So here I'm importing the libraries, I'm preparing the configuration file, and these are the two data loaders. So this is a transform for the teacher. I'm following the naming convention for Dino, so I'm calling the two networks teacher and student. The light augmentation will go through the teacher network. The strong augmentation will go through the student network. And I'm preparing 4 loaders, the train for the teacher, the test for the teacher, train for student, and test for student. And I'm also turning off the shuffle just to make sure I'm passing images in the same order to the teacher and student networks. So here's a plot of the first 10 images from the train loader teacher, and here is the train loader student. So it's the same images, but I'm just cropping large areas from the images. And the BIT architecture, batch embedding through a convolutional layer. And this is a transformer block, normalization layer, tension layer, normalization, and MLP. And at the end, I'm designing a head just like SimCLR paper. It will map from the embedding dimension of the vision transformer to the tensor of dimensions 128 dimensions. So this is what I'm doing. I'm passing the images and a batch of 128. 128 the batch, 64 is the how many patches inside the image, and 256 is the embedding dimensions. So, and here's the thing, I'm heavily changing the parameters for VIT. So the VIT parameters here, I'm just making them very light to make the vision transformer run on Kaggle notebooks. I'm using 6 layers, which is very unusual. In self-supervised learning methods, they usually use 12 layers or sometimes 24. I'm also using the embedding dimensions 256. This is usually 700 or more. So I'm making some compromises here and there. And this is a projection head which will project from the embedding dimension to the projection dimensions, which is 128. So this is what I'm going to get at the end of the vision transformer. So I'm initializing the model student and model teacher with the same parameters. And I'm running the training loop with the stochastic gradient descent turned on for the teacher and for the student. So here I'm initializing the optimizer for the teacher and student, and I'm making the gradient 0 for teacher and student, and I'm stepping for the teacher and student. What I'm doing here in the loss, I'm using the same loss from Dino V1 paper. So if you go to Dino V1 paper, you go to the pseudocode. So the student output will be log softmax, and the teacher output will be just softmax. For the student, I'm using log softmax, and for the teacher, I'm using softmax. And I'm multiplying the values and taking the mean of these values, and this will be my loss. So when I'm doing stochastic gradient descent for both for the teacher and for the student, I got a collapse. So this is the loss, just collapsed from the second epoch to 0 and never recovered from there. So why I'm getting that? Why I'm getting the loss just collapsing to zero. It's a bit explained in this paper, SimSIA paper. This is very close to what I'm getting in my experiment. So without stopping the gradient, the loss collapsed to zero, which is the red line here. And they explained that we discovered that the stop gradient operation is critical. So let's stop the gradient in the teacher network and see what happens. So this is what I've done. Training loop with SGD stopped for the teacher network. So I removed this line and commented out this line, the zero gradient. And I also commented out the gradient step. The loss, they did not go to zero. This becomes clear because I'm not updating the parameters of the teacher. I'm not changing the parameters of the teacher. I'm just updating the parameters of the student. So the parameters of the student do not have a direction to go to, but at least I'm stopping the gradient from collapsing into zero. How to update the teacher? In Dino V1 paper, if you go to this section, teacher network, this is how they updated the teacher. So the parameters of the teacher, theta t, will be mu times theta t, the old parameters of the teacher, added to 1 minus mu, the parameters of the student. Also, these solutions for preventing collapse are summarized in a good way in IEEE issues section, the GitHub repository. So this is one of the authors of IEEE. He said, in this work, we rely on asymmetric architecture between the target and context encoders to prevent collapse. Specifically, we do not propagate the loss through the target network and update its weights through the moving average update. So these are two solutions introduced here. The asymmetric architecture between the teacher and the student, and number two is updating the teacher using moving average. Let's copy the parameters to the teacher network and see what will happen. So here is the training loop with the student parameters copied over to the teacher network. I'm commented out this line. So the zero gradient is 0 point because I'm running the teacher with no grad. So I'm stopping the gradient for the teacher and I'm also stopping the step of the teacher. And at the end of each epoch, I'm copying the student parameters over to the teacher parameters. So the model of the teacher will be loaded from the state of the student. So let's see how this affects the loss. So the loss is moving to the right direction. We're finally optimizing the loss. We're not staying in a constant. We're not collapsing into zero. We're finally optimizing the loss. I know 10 epochs is not a good way to judge the loss, and CIFAR-10 is a very small data set, but based on the two previous experiments where we use the same data set and same number of epochs, well, at least we are improving on these two experiments. Of course, this is not the solution. The solution is to, as indicated here, is to use asymmetric architecture, which is I'm not using here. I'm just using two identical vision transformers for the teacher and for the student. Also, I'm not using the moving average update. I'm just copying the student parameters over to the teacher. The right way to do it is just use lambda to control how much of the teacher parameters and how much of the student parameters, and make lambda goes from 0.996 to 1 according to a cosine scheduler. One last thing is, in this experiment, I was testing the singular values of the dimensions on the projection layer. So applying this VD to analyze MLP projection dimensions, I was trying to replicate this figure from the arXiv paper. This figure here, figure 2. So what they have done, they put out the output of the two-layer MLP projector, which has the size of 128 dimensions. They apply the covariance matrix, and they apply singular value decomposition on the covariance matrix. And they plot the singular values, actually the log of singular values, and they got a collapse in the singular values. So they got this huge drop in the singular values. I was trying to replicate that. So in the architecture of the vision transformer, this head here, I was trying to get the output of the head from the test set, because this is what they have done. They are using this SVD plot on the validation set. I passed the student test samples to the trained student model. So 10,000 samples, 65 patches, 128 dimensions. So I'm dropping the class token to make this 64 times 10,000 will be 640,000 by 128 dimensions. I computed the covariance matrix and applied SVD to this matrix, and this is what I got. So yeah, this is the code. So here I'm passing with touch no grad, I'm passing the test loader to the student, and I'm computing the SVD on the covariance matrix. So this is with the stochastic gradient descent turned on the teacher network. This is with the stochastic gradient descent turned off for the teacher network, and this is after copying the parameters of the student to the teacher network. And here's the thing, I don't notice a difference, and I don't have this huge drop. I might be doing something wrong along the way because I'm doing different architecture. So in arXiv paper, they are using the negative pairs and positive pairs, and they are using contrastive learning. And I'm not using that here. I'm following the Dino V2. So no negative pairs, just two vision transformers running this thing. Just let me talk briefly about why do we need this SVD plot. So this SVD plot tells us the importance of this dimension. So if this dimension has a huge standard deviation, and why they are using standard deviation, because standard deviation measures the spread out of the points along that dimension. And in machine learning, if that dimension can spread out the points, it's considered as a useful dimension. So this is what we are trying to measure here, even in SimCM paper. So if you go to SimCM paper, here they are in the middle, the per channel standard deviation of the L2 normalized output, plotted at the average standard deviation over all channels. So for the 128 dimensions, for each one, they are measuring the standard deviation, and they are taking the mean standard deviation. So this is without stopping the gradient. They don't have any spread out of the points, and this is after stopping the gradient. They have standard deviation, so the points are spread out, and they are finally utilizing the dimensions. But the sad thing, I'm not getting this a huge drop. The only thing I noticed from these 3 experiments, in the last experiment, when I'm copying the student parameters, I'm getting 2 dimensions of equal importance. So these 2 points close to each other, indicating that these dimensions are equally important. That's it, guys, for today's video. This was an attempt to collapse things. I hope it was helpful. I'll share this blog post in the description below. Thanks for watching. Bye.